Okay, the next speaker is Mark Girolami from Imperial College, whose title I forget for the second, but it's there. Okay, over to you.
Well, I'm not sure how to follow that. No sport here, I'm afraid. So what I wanted to do, and I think this follows on really quite well from the previous speaker and all of the previous speakers, in that the one thing, the one word that has started to creep into most of the presentations is the word data. Data analysis, data analytics, data science, data munging, data wrangling, big data, small data, intelligent data, whatever. And so what I'm going to just present to you is this whole idea of data-centric engineering, and whether this is just another piece of hype or in actual fact there is some solid substance behind it. So first of all, let me just say that so I hold a chair in statistics in the mathematics department at Imperial College, but I'm also the director of the Lloyd's Register Foundation programme on data-centric engineering, which is based at the Alan Turing Institute. And so I want to just focus on a couple of examples which really emphasise that mathematics and the mathematical sciences, and so therefore I would include mathematical statistics and computational statistics, is absolutely essential in this data-driven and data-rich time that we are facing for all modern economies. So the Alan Turing Institute, so for those of you who have been asleep for the past 5 years, probably haven't heard of it, but it is the UK's National Centre for Data Science. And the Lloyd's Register Foundation, well, it is the charity arm of the Lloyd's Register Group, whose main mission is to protect life and property. And they are supporting engineering-related research at the Turing Institute based on this technology foresight review that they commissioned in 2014, which was reporting on what would the impact of the era of big data be on the engineering professions. So this is the program that I am leading and developing. I really found this, from the description of today's meeting, really quite exciting. As a statistician, seeing things like uncertain data-rich world, which industry now confronts. So I every day in what I do in my research and in my interaction with industry and commerce, there is absolutely no doubt that despite us being in a data-rich world, it's a very uncertain one. And because of that, we then need to be able to account for that uncertainty. And that's one of the major planks of the research of my own group. So what I want to do is introduce you to 2 specific examples of where research right at technology readiness level 1 and 2 was undertaken, and then it moved right through to technology readiness level 9 and is now a commercial product, a commercial process, and reasonably successful. And so I think that these are good examples of what this meeting is all about. So from research to commercial products. So the first case study is some work that I did with a company called NCR, National Cash Registers. National Cash Registers has been in business for well over a century. It was actually the precursor to the mighty IBM. And as their name suggests, National Cash Registers, they make cash registers. And have done so for quite some time. But the area of financial transactions that the NCR services that I'm going to focus on today are ATMs, automatic teller machines. And strangely enough, today is the 50th anniversary that the first ATM was actually put into operation in Enfield in London. And the first user was Reg Varney. Those of you of a certain age will probably recognise that name. So we're going to look at this as a service, a financial service, the ATM. So what was the commercial challenge that National Cash Registers came to me and to my group trying to look at and to address? Well, from a number of the markets that they were operating in, and not so much in Europe or the Middle East, but mainly in the Far East markets, the banking customers were wanting what was called a recycling facility. So in other words, somebody could deposit currency of any denomination into a machine, and rather than that currency then being segregated and manually checked by the bank for validity, so in case it's perhaps a counterfeit or it's just been through the washing machine so many times it's going to fall apart, they would like to be able to recycle the notes. So notes that are deposited could be validated in the machine and could then be made available for withdrawals as well. So this whole idea of recycling. Now, of course, this is a great thing for the banking system. However, it's also a great opportunity for those who have malfeasance in mind. And here you can see, a very recent report, of someone in a bank in China, trying to deposit, 1,000 very high value denomination bills. India, again, has one of the major problems with counterfeit currency and the actual distribution of that. And so this was the major issue. We would like to be able to offer our customers the ability to recycle notes that have been deposited, but we also want to make sure that the possibility of actually introducing counterfeit currency into the machines and subsequently into the local economy would be minimised as much as possible. And likewise, we would not want to add a great deal of cost to the actual machines themselves. So no high-priced, no high-value camera systems or what have you. We would want to use very simple sensors. So the sort of technology that's typically used is what you see here. So the very standard security marks and watermarks and holograms and so forth that the issuing banks, economies will actually place onto the bills themselves. Now these are fine if you have machines, automated machines, that are designed specifically for these particular security features. Now, if you're a company like NCR, who happens to be the world leader in ATMs, then having this currency validation system that's going to support all of the currencies in all of the countries that the machines are shipped to is going to be a horrendous logistical challenge and an extremely costly one as well. So the whole idea of automated verification and validation, as I said, has to support very large diversity of banknotes and particular types of currency globally. So we can't have handcrafted specific points of reference for specific types of banknotes. The other thing is that there is geographical variability of the quality of notes, depending on, for example, whether you're in a humid climate or a non-humid climate. And probably one of the biggest things is that any intelligence about the characteristics of potential counterfeits that would be attempted to be deposited into machines is limited, and furthermore, until a counterfeiting ring actually gets started using whatever equipment they're using, there is no information at all. And so the standard paradigm, which would assume that there are representative samples of genuine and counterfeit notes, falls down. And so the great healer of all problems, deep learning, is something that just can't be used here. And handcrafted templates are inflexible and extremely expensive to support. So NCR made the mistake of coming and talking to a statistician. And so the first thing that we said was, well, why don't you consider this as a sequential hypothesis test? It means that we then have a statistical template which can accommodate the variability of the quality of notes. It's completely agnostic to what type of banknote, what type of currency is actually being deposited. And so therefore this template can adapt in a local manner. And furthermore, we then have the whole statistical machinery to be able to make objective assessments of what would be the potential rate or expected rates of false positives, false negatives, and that would then allow the banking operators to be able to define levels of risk in terms of whether they find the level of risk of accepting a counterfeit note much less than the risk of upsetting a customer for denying the input of their money to the machine. And of course, it also means that, unlike the handcrafted templates, because as soon as a new banknote or new security features are introduced, then new templates have to be created. Here, on the other hand, all we need are the new banknotes, and we can then just bootstrap the estimation of these templates in an automated and localized way. So how did we do it? Well, we looked at the color of money. It's always a good thing to do. And because we were constrained to use extremely simple sensors, so very narrow band, pretty much LED quality sensors, we just looked at what would be the distribution of certain colors or certain responses to the particular bandwidths that we were monitoring in certain areas of the note. And so we could look at a number of different bandwidths, and we could then have a multivariate histogram which would capture the color characteristics of that banknote. And once we've done that, then we can use really modern-day, high-tech mathematical statistics from the 1930s. And in essence, what we did is we used, this is probably not schoolboy statistics, but it's not far off, where we basically just use the likelihood ratio test. So the supremum over a set of parameters characterizing some likelihood function under the null hypothesis that the notes are genuine versus the likelihood, the maximum likelihood of the alternate hypothesis that this particular banknote is inconsistent with all previous banknotes that have been observed. And some asymptotics showed us that, in actual fact, we could build our template by simply estimating a probability distribution function. And that estimate could be updated in a coherent manner. And we just used very classical statistical methods to characterize this statistical template of the multivariate distribution of the colour of the banknotes. We then got a little bit more sophisticated, and we used some mathematical statistics from the 1980s. But what we did is we said, let's really increase the power, right, the discriminating power of these tests by using multiple areas, multiple components, multiple regimes in these images, and we can do that very inexpensively. We need to use some global optimization theory, and we need to use some mathematical statistics that came out of Stanford in the 80s, using bootstrap resampling to obtain the levels of threshold to assess whether these particular statistical hypotheses would be accepted or rejected. And that was the work that we did. And in 2004, we published a paper in Pattern Recognition, a very nice journal, and everything was great. TRL level 2, tick. What happened next? Well, someone mentioned about the companies hiring the postdocs, and that's exactly what happened here. NCR hired the postdoc that worked on this with me to develop the technology. He then went to NCR, started to develop the technology, pushing it through the TRL levels from proof of concept to prototypes and to the various checkpoints along the TRL. And this whole thing was a very slow process. And even although there was a real commercial race on to have a product or a service for customers to allow them to recycle currency, this basically took almost 10 years from the first paper being published in the proof of concept to an actual product. And now, I mean, it really gives me a kick that, you know, if I look at the latest generation of National Cash Register ATMs, they have, where is it now? NCR self-serves cash deposit and recycling modules validate every note twice before accepting or crediting to minimise the risk of counterfeit notes. And that all stemmed from some work that we did and produced, you know, a journal paper, which was really quite nice. And so that's a really nice example of taking some mathematical statistics and pushing it right through the TRL process to actually delivering something that is a competitive commercial product. I'm going to give you a very quick example, a second example, where we still have to go through the TRL levels, but this is compressed substantially. And so NCR, being a century-old company, we go to Amazon, which is certainly not a century old, but is a very high-tech or digital-born company. And Amazon came to me and asked, they were wanting to improve their service to customers in terms of delivery. And the key point here is that to improve delivery and customer satisfaction, their fulfillment centres need to be serviced in an extremely efficient way. And so what they asked me to look at was, how do we improve the forecasting of demand for the tens of millions of products that we hold. So here is some data that I was using. So I spent 3 months working with Amazon on this. Now, I can't tell you what the product is. I think you can guess what geographical region we're operating in here. But basically, each of these little dots is the demand for that particular product in a particular US city. Now, unfortunately, that's all I can tell you about that work. But what I can tell you about is some other work that I'm doing, which is exactly the same in many ways, where we're looking at retail activity in London. And again, the questions are exactly the same. How much, in this case it's not stock, but how much floor space should a particular commercial outlet hold in a particular region? The mathematics that we use is pretty, well, once it's all wrapped up, it's not pretty standard, but it's a very classical spatial interaction model where we have a flow of something, so in this case, commercial activity, from some originating region to a destination region. And using maximum entropy methods, we can define what the functional characterization of the flow from one origin to a subsequent destination. And what we've been using are stochastic differential equations to look at the way in which, in this case, commercial outlets will either grow or shrink. So will either be profitable and grow in profitability or not. And I'm not going to go into all of the gruesome details of how we do statistical inference using data from London commercial activity. But suffice to say, some of the most exotic Markov chain Monte Carlo methods with having to deal with doubly intractable characteristic measures is something that we've been having to develop. But I should also say that a slight variant of all of this work is now being used for product demand forecasting. And here are some things here. So this is London, the retail outlets. You can see Oxford Street here. And this is just one draw from the Boltzmann distribution of that Langevin diffusion. And what you're seeing here is, the upper and lower quartiles of the range of growth or shrinkage, as the case may be. This is also with airports in England. How much passenger throughput can we expect in these, and therefore, in terms of planning and development of policy for investment, the characterization of these forecasts and the levels of uncertainty, which are coherently calibrated by the data, is something that's of great use for companies like Amazon. So let me just conclude by going back to the question, data-driven engineering, is it hype or hope? Well, I would say that in the era of data science and data analytics and big data and machine learning, which for me just seems like mathematical statistics and computational statistics, there is certainly a huge amount of hype. But I would also say there's a lot of hope as well, and I think this meeting really represents that. And in the programme that I'm leading for the Lloyd's Register Foundation, we're working with a large number of companies. Siemens, looking at developing predictive maintenance schedules for whole populations of their gas turbines. Working with Network Rail, monitoring structural assets such as bridges and viaducts and so forth. Shell, National Grid, and on it goes. And each of these are problems that have their roots in mathematical problems. And the one that really excites me is a little company from Amsterdam who, over the past decade, have been working on 3D manufacturing, and they are now at the stage where they are 3D manufacturing, so they are printing a bridge, a pedestrian bridge across a waterway in Amsterdam. And the city of Amsterdam is going to make this quite a big civic attraction, this 3D printed bridge. So the problem is that the material properties of metal that's been 3D printed aren't well known. The structural integrity of a load-bearing structure that's been 3D printed is largely unknown. And so what we're doing is that we are embedding these fibre Bragg grating sensors, so whole networks of them, in the structure so that we can gather data to understand and to learn what are the structural and material properties. We've been developing a digital twin or a finite element style model to really try and understand what the characteristic properties are. And also, the way I describe it is that we model pedestrians and how they're actually moving over time and using this bridge, using video cameras, and what the pedestrian impact will be on that structure. But for the purposes of marketing, it's said that we're doing machine learning. Well, whatever. But the key thing is that I think that in terms of mathematics for a modern economy, what we're doing here by supporting engineering, trying to address, and engineering companies trying to address contemporary problems with foundational mathematics and foundational statistical science is a great hope, I would say. So thanks very much, and I think there's 5 minutes left for questions.
Okay, thank you very much, Mark. So again, open it up to the floor for questions. Yes.
Another economics question, I'm afraid. Big data seems to me to give an advantage to firms that are already in the marketplace because they have a great deal of data, possibly to the detriment of new firms. In the medium term, that would imply a less competitive economy because new entrants, which are often the lifeblood of change and innovation, might find it harder to compete with existing people. So do you think we need some sort of new paradigm whereby existing companies are forced to share data with possible entrants so that possible entrants would find it easier to break in with new ideas, new technology, etc.?
So I think that's a really good question. And I think you actually have to separate companies into ones that are what are called digital born and ones that are not digital born. And so if we focus on digital born companies such as Amazon, such as Facebook, and Google and so forth, then clearly they do have the lion's share of data, and it is indeed an inhibitor into their markets. And so they definitely have monopolies. And they're not going to share the data, but in a kind of benevolent way, they do give data out to research or even to small SMEs to help them try to make sense of the data that they have. The non-digital born companies, so if we think of the traditional manufacturing industries, they've had big data for gazillions of years. I remember Sir David Cox telling me, he worked for the spinning mills in the late 40s, and they were measuring the tension in the cotton, and they were measuring the thickness and so forth, and they could do this at enormous rates, and they had so much data they had to think of clever statistical ways of compressing this and so forth. And so a lot of the traditional manufacturing industries do have lots of data, historical data, and don't know what to do with it. And of course, just because you've got a lot of data doesn't mean that you've got a lot of information that's useful or could be monetized in any way. And I think this is one of the things that some sense needs to be put into this thing that, we've got big data. It's like medicine in many ways. Medicine is producing lots of data. It's just producing lots of data in the wrong dimensions.
Okay. Question. Okay.
Hi there, thanks for that. It's really interesting. I wondered if, given that some of the maths you were saying is potentially school level, albeit quite hard. I wondered if really there's...
I was only joking.
No, I think some of it was. I mean,
I'll see about that.
Potentially. Well, that's really my question. Is there any potential there really for pupils, perhaps A-level pupils, to be involved in this and actually making a real difference to the field in the way that some pupils are starting to do in science? I wondered what your thoughts might be on that.
Well, I think you see stories in the newspapers on a fairly regular basis of 10-year-olds, 15-year-olds writing an app for something, and that app is typically using, some statistical, accounting method or what have you, that actually turns out to be extremely useful. And I think this is one of the issues here is that as active, researchers in the mathematical sciences, a lot of the problems that come from commerce and industry can be solved by schoolboy mathematics and schoolboy statistics. Quite a number can't, but quite a few can. And I think that the secret is being able to see just exactly in terms of what the constraints are, what the lead times are, what is the most optimal potential solution. But yes, I think if you had some... if you're teachers who were passionate about this, it wouldn't take much to have school-type hackathons. Say, here's a problem. Given your school maths, let's try and figure out a solution.
It's just that I knew Professor Becky Parker's doing this sort of work with her, I think, Institute for Research in Schools, and I wondered if there was some potential there. Might be quite interesting.
Well, I'm absolutely sure that there is, and so, yeah.
Okay. Someone right at the back.
Thank you. In the interest of time, I'll be a short question, although the subject is quite deep. Do you look into the blockchain technologies and cryptocurrencies?
Yes, so in the data-centric engineering program, we have just commissioned a foresight review on the use of blockchain technologies, not just for finance, but also for the engineering professions. So in maritime engineering, for example, where a ship has a very complex bill of materials and the supply chain for structures like ships and so forth is extremely complex. And it's also extremely prone now to cyber attacks. And so blockchain is indeed one potential technology. So a report is going to be coming out from the programme pretty soon on that.
Julian down the front.
Is there any evidence about the relative popularity of statistics and other areas of mathematics in terms of this question of the problems of people not taking up mathematics enough? And I just wonder what the relative kind of attractiveness was.
Well, I'm reliably told that statistics is now the number one job or requirement for the number one jobs, and I believe that the new number one highest desirable job is data scientist, which for me is statistician. So I think that it's, in terms of, it depends, at the undergraduate level, when people are studying mathematics, then I don't know what the interaction is between, or how popular statistics is with mathematics and so forth. At the master's level, certainly there are an awful lot of very strong master's programs in statistics at Oxford, Imperial, and so forth. And these are very well taken up. And then at the PhD level, I don't have any figures, but there is evidence to suggest that statistics is now being seen as a brand of mathematics that is actually quite exciting. And this may well be because we are in an age of data and computation as well.
Okay. Any final questions? No? Okay. Well, let's thank Mark again. Fantastic talk. Thank you.